Hello everyone, and I am Gaurav. And in this video, we are presenting our course project on Raman effect. So here we look at the spontaneous Raman effect, which was discovered by the C.V. Raman in 1928, and this is a phenomenon in spectroscopy where a material scatters the incident light, and the scattered light have different frequencies from excitation sources. So this leads to the observation of two type of components, which are Stokes and anti-Stokes components. So in Stokes components, so these are the Raman scattered photons that have lower frequencies than the incident photons. They result from the observation of the energy by the samples. The Stokes lines are typically more intense because the thermal energy at the room temperature favors the transition to the lower state energies. And the another one is anti-Stokes components. So these are the Raman scattered photons that have higher frequencies than the incident photons. So these results from the emissions of the energy by the samples. So anti-Stokes are typically much weaker compared to the Stokes lines because they require the samples to be in higher energy states, which is less probable at the room temperature. So here is this diagram which showing the Raman scattering medium, and there is a incident light of frequency omega, and we get scattered light of two frequencies which are omega s and omega a. So here is another one figure which shows the transition between the states. So from this diagram, we can easily understood the Raman properties of the Raman scattering. So in Raman-Stokes scattering, there is a transition from the ground state Z to our final state N by the mean of virtual level associated with the excited level N dash. So in Raman anti-Stokes scattering entails from a transition from N to ground state G with a serving N dash as an intermediate level. So we discussed earlier, anti-Stokes lines are typically much weaker than the Stokes lines because, like in thermal equilibrium, the population of the level n is smaller than the population in G by this Boltzmann factor e raised to power omega n G by kt. The significance of Raman effect in spectroscopy lies in ability to probe transition that would typically forbidden in the one photon process. Like for instance, in this figure, Raman transition like it's necessary for both the matrix, and these are the two matrix to be non-zero, and this condition implies for material system possessing the inversion symmetry and consequently energy eigenstates with definite parity. The initial state G and N must have the same parity, and however, in some cases, the transition from Z to N is normally forbidden in single photon electric dipole transition because this element must be zero. Now we will have a look at the differences between the stimulated and spontaneous Raman scattering. So firstly, we'll differentiate on the basis of efficiency. So in stimulated Raman scattering, we use a intense laser beam, and 10 or more percent of the energies of the incident laser is converted to the Stokes frequency. And without laser beam, that in the case of spontaneous Raman scattering, even for the excitation of the condensed matter, the scattering cross section per unit volume of for Stokes scattering is only approximately 10 raised to power minus 6, and the Now we will differentiate on the basis of emission pattern. So the spontaneous process leads to the emission in the form of dipole radiation pattern, where stimulated process leads to the emission in the narrow cone in the forward and the backward direction. So thank
Now, to understand the relationship between spontaneous and stimulated Raman scattering, we need to look things from the point of view of number of photons per various field modes and start with a postulate which says that probability per unit time that a photon will be emitted into a Stokes mode S will be directly proportional to the mean number of photons in the laser radiation and mean number of photons in the Stokes mode by stimulated Raman scattering, which is Ms, and spontaneous Raman scattering, which is unity. So the formula becomes Ps equals to D into ml into addition of mean number of photons, which is Ms plus 1. Where D is the proportionality constant, which depends on the physical properties of the material medium which we are using. Um, Further, now by the definition of PS, which is the probability per unit time for emitting a photon into Stokes mode, it can be said to be the rate of change of mean number of photons in the Stokes mode, and thus PS can be equated to dms by dt. Uh, If we now assume that a Stokes mode is corresponding to a wave traveling in the positive z direction at the velocity c by n, where n is the refractive index, we can say that the spatial growth rate of mean number of photon in Stokes mode is equal to the time rate change of mean number of photon in Stokes mode divided by the velocity, which is c by n. So our net formula becomes this. Uh, Now we take two opposite limits, one for spontaneous and one for stimulated, which is ms, mean number of Stokes mode photons in Stokes mode very less than 1, and mean number of photon in Stokes modes very greater than 1. So for the case of ms very less than 1, we can approximate the factor of ms plus 1 as 1 and then integrate on both the side and with respect to z, and we get this formula for as a result, which says that the Stokes intensity increases in proportion to the length of Raman medium, which is the total molecules exposed in the interaction region because of the cross section area. Now for the other case, we can take the ms plus 1 factor as ms and integrate with respect to z. This time we get a exponential factor which we wanted as a result of the stimulated scattering in the first place. This factor depends on the number of laser photons, uh, mean number of laser photons. Now we can derive a relationship between this factor G, which is called the gain coefficient, and the cross section area, which we got from in the spontaneous case. So we start by using the relation of ml to get the value of t in terms of cross section area, which is present here in the formula for G. So spatial change of ml can be written in two ways. One, by seeing it from the point of view of ml changing because of the loss because of Stokes mode radiations. So this is by accounting for the possible non-uniform angular distribution of Stokes modes and total number of modes into which the system can radiate. Another one is by seeing it from the point of view of cross section on how much area is exposed to the laser radiation which we are using. From these two equations, by equating these two equations, we can get the formula of T in terms of cross section area. Substituting this formula of T which we got into the gain factor formula, we can get the gain factor um, in terms of the cross section area changing with respect to the frequency. Now we will express this gain factor in terms of the laser intensity which we are using. Uh, and according to this diagram, the intensity is equal to the number of photons contained in the region multiplied by the energy per photon and divided by the cross section area of the region and by the transit time through the region. And the final formula which we get is expressing the G in terms of differential spectral cross section and the laser intensity, which are the two things we can control experimentally. And thus we have derived a relationship between the gain coefficient and the cross section area, and these two accounts for the stimulated and the spontaneous Raman scattering respectively.
Hello everyone, my name is Nikhilesh and I'll be discussing with you this section which is stimulated Raman scattering described by the nonlinear polarization. So what we have here is a classical conventional model to explain the stimulated Raman scattering, and to maintain simplicity, we'll just limit our approximation, just limit our analysis to scalar approximations. So what we have is here is an optical field which interacts with the vibrational mode of a molecule, which is described by this. The entire system is described by this simple equation right here. Just omega v is the vibrational mode, gamma is the damping constant, and force is the F tilde is the force which gets acted upon the system by the external optical field, and m is the reduced mass. So initially in our earlier classes when we discussed the centrosymmetric and non-centrosymmetric crystal cases, what we had was the optical field interacting with electrons there, right? And the polarization there was given by n times the electronic charge times the position of the electron. So what we have here is similar, but instead of the electron charge, as we are interacting with the molecule, we'll have a polarizability, optical polarizability. So just the optical polarizability will depend upon time. As the distance between the atoms is changing, so we'll just have a scalar approximation of this alpha t with respect to the initial equilibrium point, uh, and we'll have a term which is dependent on the generalized coordinate, and as the generalized coordinate varies with time, the polarizability will also vary with time. So as the optical wave propagates in the medium, it will experience a refractive index, and that is also changing with time. As the permittivity changes with time, and a refractive index is equal to the under root of permittivity, and the permittivity is given by this expression right here. So that's the refractive index, and as the optical field propagates through the medium, it will be impressed upon two side bands. So at the end of the medium, we'll get we'll get two more frequencies. We'll get two more waves with two more frequencies. So what we'll have is a sine band with omega L, and two other we'll have a center omega L, and we'll have its side bands which will differ by omega V. And so the polarization for a single molecule is given by epsilon times polarizability times the electric field, and the energy required to establish this oscillating dipole moment is given by half times the time average of the polarization times the electric field. So we will plug in this polarization right here, so we'll get this expression, and we could also write the energy required to establish this dipole by half times the displacement times the electric field. So it could also be given by that. So we have to derive the displacement field, which is epsilon times E, and epsilon is given by this thing right here inside. So we'll get the same expression essentially. So we'll just plug in this value and we'll get energy to be this, and so the force is the derivative of the energy with respect to the generalized coordinate. So as we do the derivation, this term goes to 0, left with this. Yeah, so just time average of E square. And so what essentially we are doing is this picture right here. So in the Raman scattering, what we have is a omega incident laser field omega with omega L, which interacts with vibrational mode of the molecule, and which gives us two side bands, omega S and omega A. And what we do in this section is just you with the laser field omega L, we also have a Stokes field, which we incident upon this, and the interaction of these two omega L and omega S will give out an intensity which also varies with omega V right here. So this will lead to the enhancement or the optimization of this omega V, which will further uh, optimize the formation of this omega S right here. Yeah, so these two are mutually enhancing processes, and just will quantitatively describe these ideas in this section. So what we have, so the electric field is given by AL and AS. These two terms right here, this epsilon, uh, uh, this E exponential two exponential terms, just propagating terms, and so we will just plug this into this expression for force here, and we'll get the time averaged parts of this. We'll just get two components. Yeah, so this and its complex conjugate. The rest two will go to 0. And so as we plug this force into this equation or initial equation, we'll have to form an ansatz for the generalized coordinate q, which is given by this and its complex conjugate. So we'll get the amplitude of the generalized coordinate, uh, this expression, and so the polarization of the bulk of the medium is given by the number density uh, times the polarization of the individual molecule. So it is given by this, and we'll just consider this whatever multiplies with this term right here outside the brackets, and that will be just the nonlinear polarization. Yeah, so just expand this q tilde right here into this electric field into this. And so now we'll consider the Stokes component of the nonlinear polarization, which will have a amplitude and and this exponential term, time varying term. So uh, yeah, so we'll have to multiply uh, the complex conjugate of this term times AL. Yeah, so that will give us an omega S component, right? Yeah, that will give us. So the amplitude term will be given by this term right here, and we'll expand the q star term, which will give us this, and the polarization amplitude is this, the multiplication of these right here. There are three fields, right? That's why the Raman scattering is Raman stipulation is a third order process. Three fields are multiplied here, so that's why it occurs in a chi3 crystal. So the chi3 is there's a so the expression used in voids takes a six term right here, which gives us six term in the denominator of the Raman susceptibility. So when we divide this two expressions right here, we'll get this term for the Raman susceptibility. So as we vary the Raman susceptibility with the Stokes frequency, we get this kind of graph. So I've made this graph right here. Just the code is intuitive. So whatever is between 0 and 2, that's the picture for the Raman susceptibility uh, of the Stokes field. Yeah, that's it. Yeah. So mm, we could approximate this denominator near the resonance field, The resonance condition is omega is equals omega L minus omega V. And so what we find out here, uh, so here the imaginary part is negative. When we take the complex conjugate of this denominator, we'll find the imaginary part of the Raman susceptibility of the Stokes field to be negative. And when we plug this polarizations right here and the initial electric fields that we used here, here, so we'll get this evolution term with respect to the z axis right here. So here alpha is given by this term, has minus sign here, and there's a minus sign in this expression as well, and the chi r also has a negative uh, imaginary term. So the negative imaginary term will contribute to the evolution, to the contribution of the real part evolution of this term right here. So that will be positive. Yeah, so that will be positive. So that will be positive. So the Stokes field will experience gain. It will experience exponential growth. So further, and there's not a phase mismatch term right here. There's no exponential wave vector term right here. So there's no phase mismatch condition in this. This is a pure gain process. It's a non-parametric process. So now, um, just will to find the Raman susceptibility for the anti-Stokes wave, just replace the Stokes frequency with the Stokes frequency with the anti-Stokes frequency. Get this term right here, and we'll find out that the Raman susceptibility for the anti-Stokes wave is the Raman susceptibility for the anti-Stokes is equal to the complex conjugate of the Raman susceptibility for the Stokes. So similarly, near the resonance, we could approximate the Raman susceptibility for the anti-Stokes in this way, and we'll just follow the steps that we did earlier to get the uh, space evolution of the amplitude of the anti-Stokes wave. And there's a minus sign here, there's a minus sign here, and in the Raman susceptibility term of the anti-Stokes wave, the imaginary term is positive. So multiplying all those things, we'll get to know that the actually the anti-Stokes wave is exponentially decreasing. It's getting annihilated. Yeah. So so in this expression right here, this will also give us an anti-Stokes component of the nonlinear polarization, which is discussed in this part. So when you multiply Q, yeah, it's when you multiply this term with this term, get an anti-Stokes component. Yeah, we'll get an anti-Stokes component. And just expand this Q of delta, and we'll get this term right here. And this is similar expression, like similar expression uh, that we get for a four wave similar we get a similar chi expression for a four wave mixing case. So we'll just uh, write the polarization in this way. Just take this three factor and we'll get a chi four wave mixing of anti-Stokes field right here, which we'll find out to be is the two times of the Raman susceptibility of the anti-Stokes. So there will be two polarization terms that will be contributed. There's a Stokes susceptibility, there's a four wave susceptibility. So yeah, so this thing, the first term is automatically phase matched, and this is not phase matched as we see earlier. And next, So similarly for the Stokes wave also we could get this term right here, but for this term we haven't included omega s right, omega a right here. But if we include that, we'll get a similar expression. We'll get a similar expression. Yeah, we'll get a similar expression. Just differ in these right here. Just the non-linear polarization component of the anti-Stokes field and the non-linear non-linear component of the Stokes field. They'll be similar. Just just the first term, right? There's an exponential and the amplitude term difference. Right? So we have all these relations uh, that we have seen earlier for the Stokes as well. And now just we have to find out the spatial evolutions of the Stokes and the anti-Stokes field. So we'll just plug all the electric fields and the polarization terms in this expression. So we'll get two coupled wave equations right here. So this has no phase mismatch condition or anything. This is non parametric term, but this has a parametric component in that. And just these are just coefficients. We saw about them earlier. What will be growth, what will be gain, won't be gain, what will result in attenuation. We've seen that. And this is there should be a delta right here. Yeah, there should be a delta right here. Uh, this is a phase mismatch condition, just a wave vector mismatch. Yeah. So that's it for my part. We will explore this more into the further sections. Thank you.
In the previous section, we qualitatively analyzed the Stokes and anti-Stokes coupling. In this section, let us qualitatively dive into the mathematics of it. The nature of the solution to the equations describing the propagation of Stokes and anti-Stokes waves, as discussed in the previous section, are 3.1 and 3.2. This form is a very commonly encountered form in nonlinear optics. For example, any forward four-way mixing process in a constant pump approximation has the same form. These type of differential equations can be very easily solved by introducing some new variables. For example, here we introduce f1 and f2, which are represented by equations 3.3 and 3.4. So how did we come up with this form? It's fairly simple. In equation 3.1 and 3.2, we make some manipulations. For example, one of the manipulations is splitting the power of E. We have e to the power iota delta kz. We just split it and write it in a different form. Writing this differential equation in a different form gives us a hint on how do we choose f1 and f2 star. So we plug these equations, which are 3.3 and 3.4, into 3.1 and 3.2. Doing that, we get two equations. Using those two equations, we eliminate f2 star algebraically. So the differential equation we get after that is in F1, which is represented by 3.5. So as if you observe this equation carefully, we can take a trial solution and put the trial solution in the equation to find some constraints on the trial solution. For example, the trial solution we assume here is 3.6, that is f1 of 0 e to the power gz, where g is the unknown spatial growth rate. We just take g to be some unknown. When we plug this trial solution into the original differential equation in F1, we get the following relation in G, which is equation 3.7. So if we see this equation carefully, we can see that this is a quadratic equation in G. So solving quadratic equation is fairly straightforward. So solving the equation 3.7, we get the solutions of G, which is 3.8. We'll get two solutions of it, G plus minus. And here for we have G depends on alpha 1, alpha 2, K1, K2, and delta K. So for some special values of these variables, which are alpha 1, alpha 2, K1, K2, delta K, will have distinct values of g. We'll have distinct values of g when the term in the bracket, which has a square root, is non-zero. So whenever we have a solution where we get two distinct values of f1, we can assume a1 to be this. This is just an assumption. So we assume a1 to be this. And why do we get this? How do we assume a1 to be this? So we know what will the form of f1, but f1 is nothing but this. So a1 will be fairly simple. F1 will be a linear combination of these equations. If you have two values of g, and we just take this term on the other side. So yeah, a1 is this. Now here a1 plus and a1 minus are merely constant of integration, and we can determine this constant by having some relevant boundary conditions. Here we are assuming a general case, so we do not take any boundary condition as of now. Now once we get the value of a1, calculating a2 star is fairly straightforward. We have the differential equation here. We can just plug in the value of a1 and get the value of a2 star. So doing that, we get a2 star to be this. Now we can assume a2 star also to be of the form this equation 3.1. How do we get this? Same as a1. We have this, we know what the form of f2 star. So we know what the form of a2 star. So by comparing equation 3.10 and 3.11, we get this ratio. We get the ratio between a1 plus minus and a2 star plus minus. Yeah. So here, if we see this expression carefully, we would not suspect that it has any symmetry. But here it has, because G, as I mentioned earlier, is dependent on alpha 1, alpha 2, k1, k2, and delta k. So G1 plus minus can be written in terms of these variables. Here we have not written that. So there are multiple ways to write this ratio. So let us do that first. And one more thing I wanted to mention is, how did we compare these two? So we just compare the part of the solution which grows as exponential g plus z and as g minus z. Fine. So by using equation 3.8, which is this equation, we can write g plus and g minus in various form, like multiplying them both or adding them both or subtracting them both. So we'll get various relations. So the two most important relations for our derivation are these two mentioned here. These two relations can be acquired from equation 3.8. So using equation 3.13, 3.14, and 3.8, we can rewrite the ratio which we obtained here, which is equation 3.12, as this way. If you observe the form very carefully, this form explicitly shows the symmetry between roles of omega 1 and omega 2 fields. So this is how we show symmetry. This form does not give us any idea or any clue about the symmetry, but rewriting G in some other form helps us. So this is a general case. So now let us apply boundary condition to get an exact solution. So by applying boundary condition, I mean, let us say that input fields are known at plane z equals to 0. That we know the values of the input fields at z equal to 0. So applying these boundary conditions to the above obtained equations, we get this solution. And notice one more thing, that in equation 3.17, which is A2 star, this can also be written in the form of alpha 2 instead of alpha 1. So yes, this is our final solution. But before going on to apply this solution to Raman scattering, let us now make sense of this solution. Let us now intuitively get an idea of it. So we'll apply some limiting cases and see if this equation gives us the correct solution for those limiting cases. Let us consider one limiting case, that is dispersionless, nonlinear medium without gain or loss. So for a medium without gain or loss, we set alpha 1 and alpha 2 to be 0. And as we know, if the medium is lossless and dispersionless, chi3 of omega 1 equals to 2 omega naught minus omega 2 must be equal to chi3, omega 2 equal to 2 omega naught minus omega 1. We can also see that the product into K1 into K2 star should be equal for both of the cases. So this is the value which we get when we multiply these both. Accordingly, we have equation 3.12, which is mentioned here. We can also write this equation by applying these conditions. So that equation turns out to be this. Now in the right hand side of this expression simplifies this considerably for case of perfect phase matching, which is delta k equals to 0. So, and it becomes this value. So if we, this equation reduces to this one, which we can easily see to be plus minus iota. So what this actually means is that the two frequency side bands are phased by plus minus pi by 2 radians in each of the eigensolution, which actually makes sense intuitively. So let us consider one more case of a medium without a non-linearity. If we don't have a non-linearity in the medium, it is just transmitting, right? So it is just a case of free propagation. So let us see if applying this condition to the general case we got, either it gives us free propagation or not. So if we apply the conditions of non with a like a medium which doesn't have non-linearity, our G plus and G minus reduces to equation 3.12. Now once we get this, we can see that the ratio which we obtained here for general case turns out to be infinity for the positive one and 0 for the negative case. And thus we can see that the positive root of the wave which correspond to omega 2 corresponds to this one, which is equation 3.23, and the negative root corresponding to omega 1 which propagates as this. We can clearly see that these waves simply experiences free propagation as the equation 3.23 and 3.24, sorry for the mistake here, are equations of free propagation.
So, hello everyone, my name is Meet and I'll be going to carry forward this discussion on stimulated Raman scattering, and my topic is on Stokes anti-Stokes coupling in stimulated Raman scattering. Now that we are all set up and have solved the coupled differential equations, we can use the solutions in analyzing the simulated Raman scattering. In our case, we will replace omega 1 with omega s, that is the Stokes frequency, omega 2 with omega a, the anti-Stokes frequency, and the similar logic applies to the absorption and coupling coefficients represented by alpha and kappa respectively. We know from the previous sections that the susceptibilities related to four-wave mixing and Raman susceptibilities are related by a factor of 2, whereas the omega s and omega a, the susceptibilities are related by complex conjugation, and that is uh, described in this compact equation. We will also be making use of the relations that connect the coupling and absorption coefficients to one another, that is alpha A to alpha S, kappa S to alpha S, and kappa A to alpha S star. In this expression, phi L is the phase of the pump laser described in this equation. AL is equal to mod of AL e power I phi L. And we will also be making use of the Stokes absorption coefficient, the knowledge of it, and it's given by this complicated term. Now this sets up the environment, and we can plug all these values in the general expression for the eigenvalues G plus and G minus, uh, which are uh, which are given in this equation 3.8 G plus and G minus. You can substitute alpha 1 by alpha S and alpha 2 by alpha A, and similar for the other things. And what we arrive at is this expression for G plus and G minus. uh, this is a big term, but it's considered to be a good approximation to substitute ns omega A upon Na omega S to be 1.
unity, and under this approximation the G plus and G minus simplifies to this expression: I alpha is delta K minus delta K upon 2 whole square under root, and G minus is minus of the same thing. And this is the plot of G plus G minus with respect to the phase mismatch that is represented by delta K. And an interesting thing to note here is that in the delta K is equal to 0 limit, both G plus and G minus vanishes. Um, and that is because of the strong coupling between the Stokes and the anti-Stokes field that in the delta K is equal to 0 limit. In the very now we'll consider two limits to this problem. The first is when the phase mismatch is very high, that is modulus of delta K is much greater than modulus of alpha S. In that limit, the G plus and G minus could be approximated to this values, that is alpha S plus half iota delta K, and G minus is minus of the same thing. And now we can substitute this G plus and G minus in this expression to get the ratio of the side amplitudes, this 3.112, the ratio of amplitudes for the plus or minus mode and beyond, and for the anti-Stokes and the Stokes field, and which gives us the result here. For the large delta K limit, the plus component of the anti-Stokes conjugated upon plus component of the Stokes is I delta K upon alpha S, and minus component conjugated of the anti-Stokes upon minus component of the Stokes is 0. And we know in the large delta K limit that both the differential equations almost decouple, and hence we get this results. Whereas in the very small delta K limit, that is in perfect phase matching, the eigenvalue, that is when we substitute delta K is equal to 0 in the above expression, the G plus becomes 0, whereas G minus is minus alpha S into 1 minus ns omega A upon na omega S. It's although it's a very small quantity G minus, it's a negative quantity, but it's not identically 0. And the negative nature of this is going to be used in the analysis of the solutions to the equation. And again, substituting these values in the 3.12 equation, we arrive at the side mode amplitude ratios as follows. And for both plus and minus component, the anti-Stokes upon Stokes is the ratio is -1. And we can see that eigen solution is an equal combination of the Stokes and the anti-Stokes component. Now, in the same limit, we will look at the spatial evolution of the field amplitudes with appropriate boundary conditions at z is equal to 0. That is, we know the values of these fields at the beginning of the medium or z is equal to 0 plane. And uh, we have to substitute this in the general expression for the solution of the coupled equations, and here is what we get from As of Z, the Stokes field, and the A of anti-Stokes field conjugated this factor into this first term plus the second term. Because of the negative nature of the G minus in the Z tends to infinity limit, these both terms they vanish, uh, and this is the first terms are just constant because we know the boundary condition, these are just constants, and this factor 1 upon 1 minus ns omega A upon na omega S is just an amplification term. So we can see that both these fields attain a saturation in the Z tends to infinity limit, that is they attain a constant value, which is also shown in this plot of As or A with the propagation distance Z, and they tend to rise in the beginning over several orders of distance of 1 upon G minus, but then they cease to increase and they attain a constant value. Uh, and to understand why the field amplitudes remain constant, we again have to go back to the classical model of fields interacting with the vibrational mode of the molecule represented by the harmonic oscillator. And earlier we remember that we use the field consisting of two components, the Stokes field and the laser field interacting with the harmonic oscillator vibrating at omega nu frequency. Now we will have to modify the force term by also including the anti-Stokes frequency component in the electric field, and because of that, the differential equation for the molecule oscillating, it gets modified. Yes, here the force term gets modified, and we need to follow the previous analysis exactly, like by calculating the interaction energy and differentiating by the distance to get the force term. And this E will also have the anti-Stokes component, so this will change, and hence the force term will change, and hence the right hand side of this will change. Here Q represents the internuclear distance of a molecule deviated from the equilibrium value, and again, doing the same analysis as before in solving that equation, we substitute a sample solution. This qzt is equal to q of omega into e power I big kz minus big omega t plus the complex conjugate, where big K is the KL minus defined as KL minus KS, or KL K minus KL, and big omega is defined as omega L minus omega S or omega A minus omega L. And this coefficient Q of omega is this big thing. Which we get from substituting it into the differential equation. And we can see that because of this factor in the right, AL into AS star plus AA into AL star, when we substitute the saturated values of AS and AA star in this expression, this turns out to be 0. And because of that, the q omega in the high z limit vanishes, and we can see that the vibration of the molecule ceases, and hence the fields, they attain a saturation value. And yes, I think that is it from my side.
Stokes-Raman scattering. So in this section, we will analyze both coherent anti-Stokes-Raman scattering and coherent Stokes-Raman scattering, but mostly focus on coherent anti-Stokes-Raman scattering. In coherent anti-Stokes-Raman scattering, also for short form called as CAS, there are usually two beams of different frequencies, omega 1 and omega 2. Let us consider omega 1 is greater than omega 2, and they are passed through a Raman medium, and due to this interaction, a new beam is created at a different frequency. In this process of coherent anti-Stokes-Raman scattering, an output is created at a frequency of 2 omega 1 minus omega 2 as a consequence of the susceptibility which is given. Let us further analyze coherent anti-Stokes-Raman scattering. So we can describe the susceptibility that describes the process as chi f omega a equal to omega 1 minus omega 2 plus omega 1 using this equation 5.1, which we can get from the previous sections that we have covered. The nonlinear response experiences a resonance whenever the input frequencies omega 1 and omega 2 are selected, so that omega 1 minus omega 2 is equal to a vibration frequency omega v of the material system. So we can write the coupled amplitude equation for the generation of an anti-Stokes wave as this differential equation, where we have alpha a to be this term and kappa a to be this term. This image is a graph that is of a typical Gauss line shape. We also have delta k equal to delta k dot z, that is in the z direction, where delta k is 2k1 minus k2 minus ka. So a cause is usually studied under conditions such that the generation of an anti-Stokes signal is dominated by the second term on the right hand of equation 5.2. And this situation occurs whenever the gain of stimulated Raman scattering is small. Under this assumption and that of perfect phase matching, that is delta k equal to 0, the growth of the anti-Stokes wave can be expressed as this following equation. The spectral variation of anti-Stokes generation as either of the two input frequencies is varied is determined by this expression, and thus is expected to have a shape in the form of a square of a Lorentzian function. However, when experimentally it was measured, it was found that the line shape is often highly distorted. Example of such a line shape is given in the above graph. The explanation for this behavior is that in addition to the highly resonant molecular response described by equation 5.1, actual materials also exhibit a non-resonant background susceptibility due to electronic response and to non-resonant vibrational modes. The total susceptibility is then given by chi and r is chi f over omega a, and consequently the line shape will be this expression, which leads to a line shape as shown of that in the figure.